The second step among the preferred steps or recommended steps of plotting a good graph is choosing and stating the scale. You may ask, what is a scale? How is it chosen and stated? And most importantly, how is it used in plotting graphs? That takes us to lesson number 11, and that is choosing and stating the scale. Please join me as I explain step by step using an existing table how to choose, state, and apply scale. Please follow through. Scale is simply defined as the value of one interval on the graph page. When we plot graph, we have to choose what each interval represents. Sometimes we allow it represent 1. Sometimes we allow it represent 2 and some other values. In all the examples I gave earlier, at the time I was making freehand Cartesian sketches, you saw me use a value to represent every interval. If I gave a calibration of 1, 2, 3, 4, 5 on x-axis, for instance, what it means is that every interval is equal to 1. That 1 that I wrote corresponding to the first interval is called the scale. So scale is the value chosen to represent one interval on the axis, not everywhere on the graph page. So far, let us look at the formula for choosing scale. This formula is needed because it is not a scale that I used in plotting a particular graph that will be used in plotting all graphs. The table determines the type of scale you're going to make use of. Each graph being plotted has its own scale that must be used for calibration. Therefore, each table determines the scale. In a short while, we see how this table will help us to illustrate how to choose a scale. But before then, look at how to choose a scale. The formula for choosing scale is S is approximately equal to H over C, or S is approximately equal to H over T. I choose this one over this. The reason is that in this work of graph, we have seen this C being used to represent intercept, vertical intercept. So to avoid confusion, let us not use it here, but just recall that it is here. We choose to use T. So the formula for finding scale is S is approximately equal to H over T. Let us explain what each of them means. This S is scale. Perhaps already you have known what a scale is. The symbol approximately equal to reminds us of the fact that the value of scale we're going to get must not be rigid. If there is need to approximate it to suit our desire in accordance with prevailing table, we do so. Because scale is malleable, then we do not fix equal to here. We say approximately equal to. If what you get after this calculation is okay, then you put equal to here. If not okay, we are going to approximate it. That is why this symbol is here. What then does this H refer to? It refers to the figure that is highest in magnitude for a particular variable. X is a variable. Y is also a variable. H refers to that is highest in magnitude. This slash and this slash enclosing the H should make us know that it is not just a number, but that is highest in magnitude. This is important because sometimes a number that is higher in magnitude is negative. And because it is negative, we might be tempted to start seeing it as the lowest value and not consider it for use to choose the scale. Our foregoing case will bring this to limelight. Therefore, this HE refers to the figure that is highest in magnitude for a particular variable. For instance, here, if this table contains values that are going to make use of to plot a graph on a graph page, all the values from -2 to 6 are supposed to be there. These dots simply tell us that the figures which are there are not necessary as long as they are between this -2 and 6. So far, we understand that this -2 is the lowest figure on this X, and then 6 is the highest figure. 6 is a figure that has the highest magnitude for X. Because of that, the HE for this X is this 6, which means when choosing scale for this X, don't forget that we choose a scale for a particular axis. We choose a scale for each axis separately. If after choosing scale, the two are equal, it is not a bad thing. But just to bear it in mind that each axis has its own scale, chosen with the same method, the same HE over T. If we place 6 here, it thinks that we have realized that the highest magnitude belongs to 6. So we place it here only for this X. Then next, if we are choosing the scale for this Y axis, all the values in Y range between 3 or range from 3 to 35. Here also, while using this formula for finding the scale, this H is 35 for Y. That means we choose scale twice. We choose a scale for X and a scale for Y, or choose a scale for Y and later choose a scale for X. Anyone can come first, but it must be emphasized that scales are chosen separately, one for each axis. Therefore, for X, HE is equal to 6. For this Y, your H is 35. I believe that at this point, we've had enough reason to conclude that we have known the meanings of this S approximately equal to and this H. What again? What about this slash here? That tells us that no matter what sign comes before this HE in the table, we don't think about signs. Instead, we think about magnitudes. Like I said earlier, when we go to our foregoing case, we see how to apply this. What about this T? We say T is equal to number of intervals available for use. How do we know the number of intervals available for use? We recall that in every layout, in all basic layouts, there are 4 basic sub-axes. They include the positive Y, the negative Y, the positive X, and negative X. This T is number of intervals available for use on that sub-axis that is used for choosing the scale. For instance, this X had 6 as its highest value. And because no sign is here, we remember that it is plus 6. That means that it is not minus x that was used to choose the scale. Instead, it was plus x that was used to choose the scale. Because of that, to get t, that is number of intervals, we count how many intervals from 0 to the end of the graph page, and then determine how many of them that we want to make use of. It is not advisable to make use of all the intervals available on that sub-axis. Cut off 1 or 2 intervals and regard the rest as available for use. What about t for this? How do we get it? We also remember that this 35 is plus 35. What it means is that the scale for y will be chosen only along the positive y-axis. Therefore, the t for the y-axis will be gotten by counting how many intervals from 0, that is origin, to the uppermost part, the uppermost part of that y-axis, that is the top edge of the y-axis. Then we can cut off 1 or 2 intervals and regard the remaining ones as number of intervals available for use. Now let's assume that for plotting this on a graph page, after choosing our layout, we realize that from origin to the edge of the positive x-axis, that there are only 3 available intervals. That means that t is equal to 3. Let us choose a scale for it. Scale for x-axis is such that scale is approximately equal to h over t as before. Recall I said that the highest magnitude corresponding to x is 6. That is why this h should become 6 here. And the number of intervals perhaps is 3. That is, from the origin to the right of the x-axis, there are 3 usable intervals. That is why I put 3 here. In the end, 6 over 3 is equal to 6. Therefore, scale is equal to 2. What it means is that every interval will now be equal to 2 units. That is the implication of saying that S of scale is equal to 2. Let's do the same thing for y-axis. In like manner, scale for y-axis is such that scale, like before, is approximately equal to h over t. Corresponding to this y-axis is a figure that has the highest magnitude of 35. That is why I replaced this h with 35. And this t, perhaps on the axis, that is positive y-axis. Why did I say positive y-axis? It is because 35, with which we chose the scale, or with which we are choosing the scale, is positive. If this number were negative, we're going to consider the number of intervals from 0 along the negative y-axis to the edge of the graph page. But because we are choosing scale with this plus 35, then it means that we are choosing the scale with positive y-axis. So from the origin to the end or the edge of the graph page along the positive y-axis, there could be 7 usable intervals. Remember that it is you, the one that plots the graph, that will choose the number of usable intervals. It is not all intervals available from the origin to the end that must be used. For emergencies, cut off 1 or 2 intervals. I have said that before, but for emphasis, I am repeating it at this point. Now, if there are 7 usable intervals along the positive y-axis, then the number of intervals, that is t, now becomes 7. 35 over 7 is equal to 5. Therefore, the scale is equal to 5 for y-axis, meaning that the value of each interval along the y-axis is equal to 5 units. Please, when a scale is chosen for a particular axis using one subaxis, it applies to the entire axis. For instance, if I got scale as 2 for x-axis, though I used positive x-axis, it applies to both negative and positive axis of y, of x. Also, that I chose 5 as a scale for y-axis using the positive y-axis does not mean that 5 units represent one interval only for positive y-axis. It is going to represent every interval along the entire y-axis. Let's now talk about the preferred scale. After we use the formula for finding scale, that is h over t, to find the scale, there are preferences. Sometimes, after we get the scale we got is not usable. That means that sometimes, even though we do not get the scale with the wrong formula, the value we got after calculation is something we don't want to use. That means that there are some scales which are preferred over others. So which one is a preferred scale? It is preferred that scale is a figure that makes calibration easy. That is, we remember that after choosing scale comes calibration. That is, marking every interval with its value is what we refer to as calibration. We are coming to that. When that is happening, we calibrate with the scale chosen. Without the scale, we can't give values to intervals. Then, if scale chosen is what is going to make it possible for us to calibrate the axis, what it means is that we should be careful the type of scale we choose. A scale that is preferred is that makes calibration easy. Which one is an easy calibration? A calibration that can be done without the help of a calculating device is easy. Imagine that you are calibrating an axis, and every now and then you are punching calculator to know the next value. Because we calibrate arithmetically, we keep adding the same scale. And if we cannot add it except we use calculator, it means that the scale chosen is the wrong one. Imagine that you got your scale as 7.15 as your scale. After you mark the first interval as 7.15, what do you think the next interval will be after adding the 7.15 to get the next interval? That will almost not be done except you use calculator or any other calculating device. Examiner that gives you a question on graph will not have to punch calculator each time he wants to know whether you did the wrong or right calibration. Because of that, a wrong scale is not a preferred scale. A preferred scale is that makes calibration easy. You can do the calibration without the use or without insistence on using calculating device. Therefore, the preferred scales are 1. Even whole numbers. That is, these things are the things that have been accepted by many that have practiced plotting graph on the graph page as acceptable scales. 1. Even whole numbers. Examples are 2, 4, 6, For instance, if your scale is 2, I'm sure that if you write 2, the next one is 4, the next one is 6, the next one is 8, the next one is 10, 12, 14, 16, and that manner. We don't have to punch calculator before getting the next value for the next interval. This is why even numbers are highly and widely acceptable. Number 2 preferred scale is 5 and its multiples. Though 5 is an odd number, 5 is not an even number, but we can use it for calibration. So if you get 5 as the answer after calculation for scale, and you want to use that 5 for calibration, it is acceptable. Why? We can calibrate with 5 without insisting on using the device of calculation. Why? For instance, if you write 5 as the value of the first interval, the next interval is 10. The next is 15. The next is 20. So what it means is that when we use 5 to calibrate, we don't insist on using calculating device. Because of that, we accept 5, though not an even number. The next one is power 10 submultiples of 5. We have multiples of 5 and also submultiples of 5, not just all submultiples. It is power 10 submultiples. That is, if we use power 10 to divide a multiple of 5 or 5 itself, we get what we call power 10 submultiples of 5. They are 0.5. For instance, if you divide this 5 by 10, what you get is 0.5. If you get 0.5 as the scale, it is acceptable because the next one is plus 0.5, which is 1. The next one is 1.5. The next is 2.5. The next is 3. The next is 3.5. The next is 4. What it means is that if we get 0.5 as our scale, it is usable. We also have other power 10 submultiples of 5. They include 0.05, 0.005, and so on and so forth. The number 4 among the list of preferred scales is power 10 submultiples of multiples of 5. 5 itself has multiples. These are multiples of 5, 10, 15, 20. We can also get the power 10 submultiples of 10, 15, 20 to get things like 0.15. That is, this 15 divided by 100 is 0.15, because that 100 is a power of 10, whole number power of 10. So 0.15, 0.015, 0.25, so on and so forth are all examples of power 10 submultiples of multiples of 5. They are also acceptable as scales, because if, for instance, 0.15 is a scale, we use it to calibrate the first interval, and that the next one is going to be 0.15 plus the same 0.15. That will give us 0.3. The next 0.3 plus 0.15, and so on and so forth. So because we can get these things without insisting on use of a calculating device, this is acceptable. The last but not the least is 1 and its power 10 submultiples. Though these figures can be covered in this number 2, it is important to repeat it because 1 is unique here. 1 is not an odd number, it's not an even number, and yet we are trying to mention it here that 1 can be used because 1 can easily be added to anything to get the next number. Therefore, 1 and its power 10 submultiples are also preferred scales. Example, 1, 0.1, 0.01, 0.001, and in that manner, and so on and so forth. Also, power 10 submultiples of even numbers are preferred scales. Examples are 0.2, 0.02, 0.4, 0.06, etc. Don't forget that before we considered even numbers, which were only whole numbers. At this point, we are looking at even numbers, which are power 10 submultiples. Now let's turn our attention to how to obtain the preferred scale. How to obtain the preferred scale. Since we have known the preferred scales and what they are, how do we insist on getting the preferred scale? It says, using the formula SO is approximately equal to H over T. Obtain the preferred scale by manipulating the values of H and T, if necessary. Without wasting time, let us use some examples to illustrate this instruction. Assuming that after watching a table and you see that the highest magnitude, the figure with the highest magnitude is 20, and the number of usable intervals you have seen available on the graph page is 4. 4 intervals available, the highest value of 20. The next is to choose a scale for that axis. What will you do? You are going to make use of this formula. S is approximately equal to H over T. Do it first without manipulation to check whether what you're going to get fits into the array of acceptable or usable scales. Let's see how to go about this one first. For it, the scale, that is S, is approximately equal to H over this T, where H is this 20 and this T is this 4. So 20 over 4 is equal to 5. Therefore, the scale is equal to 5. Do you think we need to manipulate in this case? The answer is no. What it means is that it is not necessary to manipulate. The reason is that 5 is among the preferred scales. Let's see another one. If on the table also we have the highest value for the axis being considered, or the variable being considered, is 17, and there are 5 selected usable intervals, we get the scale like this. Scale is approximately equal to H over T. That is equal to 17 over 5, and that will give us 3.4. What it means is that our scale is equal to 3.4. Is 3.4 a preferred scale? Though it appears to be a power 10 submultiple of multiples of even number, or even number, whole number of even whole numbers. 34, for instance, is an even number, and its first power 10 submultiple is 3.4. One might argue that from that standpoint, 3.4 is a preferred scale. I wish to tell you that though this is correct, it is not as usable as others. Let me inform you that it is possible for a scale to fall into any of the preferred categories, but as long as calibration will not be done easily with it, we discard it as a preferred scale. And that is the case with this 3.4. If you start calibrating with 3.4, before long, you start looking for a calculator to make you finish the calibration. Because of this will not be a preferred scale. What then do we do? It is time to manipulate the values of H and T. We don't advise that after choosing your T, you manipulate it. Please don't quickly decide to manipulate T. The one that we always can manipulate is the H. Anyway, In the manipulation, we choose to manipulate either H and T, or only H as the case may be, or don't manipulate any of them. Get the answer and manipulate the answer. I repeat, either we manipulate H and T, or manipulate only H, or don't manipulate any of them. Calculate it the way it is and get the answer. Then afterwards, you can manipulate the answer. What it means is that this 3.4 is not a preferred scale. Let me start by manipulating the answer while keeping the H and T the way they are, meaning don't touch 17, don't touch 5, but touch the answer. Make it up to what you want. How do I do that? This 3.4 is not a preferred scale for reasons I gave earlier. The next thing I do is that I have to push this 3.4 up to the nearest number that can make calibration easy. Even if it is 3.5 you want to make use of, that's okay. But it is always easier to start with whole numbers. The best scale is a whole number, preferred whole number scale. The next best, that is after the best being whole numbers, the next will be decimals that have only one decimal place. After this category of numbers, we have decimals that have two decimal places. In fact, once you depart from using a whole number as a scale, then a scale begins to pose a problem in being used for calibration. If it enters decimal zone, then we still prefer that it has one decimal place. If 1 dp is not possible in a case at hand, we can use 2 dp. But from 3 dp upwards, no matter how smart we are, we might need to punch calculators to get the next value during calculations. Back to what I was saying before. This 3.4 is not a preferred scale. And now I have chosen not to manipulate this 17 and this 5. Instead, I want to manipulate the answer that I got afterwards. I want to make this become a whole number. Though 3.5 and 3.6 can still serve, even 3.8 can serve. But the most preferred after 3.4 is 4. 4 is not so far from 3.4. Please, in manipulating it, don't push that number downwards. Don't make it become 2 or 2 point something. There is danger in doing that. There is danger in pushing a number lower than what it is as a preferred scale. Instead, push that number up to the nearest number which can serve as a preferred scale. Therefore, the scale is now pushed up to 4. We don't approximate scales according to the principles of approximation in mathematics. We just pin it to a value higher than the value we have, which is not a preferred scale, so that we can get what we're looking for. At this point in time, 3.4, going by the principles of approximation in mathematics, 3.4 should not become equal to 4. But based on scales, you can approximate any number to any number at all. 3.4 has become 4 at this point because 4 is among the usable or the preferred scales. Recall that this scale is equal to 4 was gotten by manipulating the answer while leaving 17 and 5 alone. Let us try to get the same 4 by starting to manipulate with either H or T or both of them. Now see what has happened. The scale is still equal to 4, but something has happened. What is it? I have been able to manipulate this H. H had been 17 before, and T had been 5. Recall what I told you earlier. I said that it is not advisable to manipulate T you can manipulate t, but don't be quick to do that. If you think about manipulating the scale at this level, think about manipulating h. Okay, let t remain the same 5. That is 5 usable intervals. But if h is equal to 17 and t is equal to 5, I know that if I divide 17 by 5, that I'm going to get a value which is not usable. For that reason, I manipulate it at this level by pushing this 17 up to the nearest value, which is not so far from 17, which will produce a whole number or any other preferred scale when 5 divides it. The nearest number to this 17, which is not so far from it, which if 5 divides will give us a preferred scale, is 20. That is why I made this 17 become 20. See it here. This h, instead of being 17, has become 20. So this 20 is by manipulation, according to our purpose here. So that when 5 divides this 20, then the scale becomes 4, just as usual. At this point, you have seen that it is possible to get the preferred scale by maintaining the h and t and manipulating the answer. It is also possible to get the preferred scale by manipulating the h or t, or both of them. Let us say the last one here. The highest value is 1, and the number of intervals is 10. Let's see. Now we have it that the scale, as before, is equal to h over this t. The h is equal to 1, and t is equal to 10. This h is 1, and t is equal to 10. So 1 over 10 is equal to 0.1. Therefore, scale is equal to 0.1. Notice what happened here. There was no need for manipulation, so nothing was manipulated. After calculation, no need for manipulation. Before calculation, no need for manipulation. Some cases of this sort exist. Just use discretion in your effort to get the preferred scale. Let's now turn our attention to how to state the scale after choosing it. Don't forget that we talked about choosing and stating scale. We just learned how to choose scale. Now let us learn how to state it, so that anybody seeing the work we've done on graph can quickly understand what we have done, though we are not there. It says, to state the scale, state how many units that one interval represents. That is, how many units of the physical quantity being plotted on the axis, which one interval represents. We continue. Do not mention the term interval. Instead, mention its assumed length. We remember that earlier I said that anytime we see 5 unit boxes in an interval, we call it 1 cm. If we see 10 unit boxes in an interval, we call it 2 cm. If we see 15 unit boxes, we call it 3 cm. If we see 20 unit boxes to make an interval, we call the interval 4 cm interval. But recall that for our case that is just going on, the graph page we're using is containing 10 unit boxes per interval, which means that our graph page is a 2 cm interval type. That is why we now wish to state the scale we are using for the case at hand. Recall that we found that 1 is the unit. 1 is the scale for the x-axis, while 4 is the scale for the y-axis. Therefore, we then state that A, 2 cm represent 1 unit on horizontal axis. It is not always safe to use the word x or to use the expression x-axis. The reason is that if you plot a graph of a table gotten from a real-life experiment, what you're going to plot on the axis will not be called x. Instead, that variable will be named accordingly. Therefore, the best thing to say is horizontal axis, not x-axis. X is only mathematical, but this word horizontal covers everything, whether it is experimental or purely mathematical. Number B, 2 cm represent 4 units on vertical axis. Like before, please don't use the word y or the expression y-axis. Instead, use vertical axis. We can summarize these things by saying 2:1. That is for this axis. That is 2 cm for 1 unit. Then this is 2 cm for 4 units. This is how to state a scale after choosing it. It is just an example. It is believed that this example is enough for you to have used to learn how to state your scale after choosing it. In practice, you learn more of it.